Hello everyone, I am Dipak from the Department of Geological Sciences, Jadavpur University. Today I will be discussing about the chemical elements, their origin and distribution in the solar system and in the earth. One of the most fundamental yet intriguing question that has haunted almost all human mind is whether the universe ever had a beginning and whether it will end at some point of time. A possible clue to the answer to this scientific question came in when Edwin Hubble in the year 1929 demonstrated that the distant galaxies are moving away from our Milky Way galaxy and the whole universe was expanding. A startling corollary of this observation is that at some point of time the whole universe must be much and much smaller, and maybe there was a single point, and from this single point the universe instantaneously expanded, and this point is known as Big Bang. Another important question that has been asked by all scientists is whether all the elements that we see today around us were formed during the Big Bang or thereafter. There is one important observation, like the hydrogen and helium content of all these stars are almost similar, whereas the younger stars have heavier elements in higher concentration. This means that hydrogen and helium were perhaps formed during the Big Bang, whereas the heavier elements formed subsequently. Now, our present state of knowledge suggests that the elements formed at different stages. In the year 1956, Burbidge et al. In a very classical paper, The Origin of the Elements in the Stars, summarized the different processes by which elements form, and this is known as polygenetic theory or polygenetic hypothesis. Our modern day understanding suggests that the different elements form at different astrophysical conditions in different parts of the universe, and depending on these very specific astrophysical conditions, the element formations are divided into different processes, like the Big Bang nucleosynthesis or cosmological nucleosynthesis, stellar nucleosynthesis, explosive nucleosynthesis and galactic nucleosynthesis. I will start with the Big Bang nucleosynthesis. This Big Bang nucleosynthesis actually discusses about the origin of element right after the Big Bang. So, at the very beginning, as all the matters and energies were condensed in a very small space, the temperature was incredibly high, maybe in the tune of 10 to the power 32 Kelvin. So, matter could exist only in the form of fundamental particles as quark soups. In about 10 to the power minus 2 seconds, the temperature became around 10 to the power 11 K when matter started condensing and protons and neutrons dominated. In about further 10 power 2 seconds, temperature became 10 to the power 9 K, and these protons and neutrons, they can started combining to form deuterium, tritium, the isotopes of hydrogen, as well as different isotopes of helium. But the temperature was still so high that the nucleus could not be combined with the electrons to form the atoms. Now, this process of formation of hydrogen and helium halted because the temperature decreased significantly due to the rapid expansion of the universe, as well as the abundance of free neutrons that declined rapidly, as the half-life of neutron outside the nucleus is about just 10 minutes. So, the first universe was then composed of hydrogen and helium. In about 5 to 7 into 10 to the power 5 years, temperature fell down to about 3000 K or Kelvin, and then electrons could combine to the nuclei which has already been formed to form the atoms of hydrogen and helium. So, the universe was then composed mainly of about 75% of hydrogen, 4% of helium and the traces of lithium. Now, thereafter, the universe was composed of gaseous clouds of hydrogen and helium, and some sort of heterogeneity was created in these homogeneous gaseous clouds comprising mainly hydrogen and helium, and when this heterogeneity they started collapsing due to their gravity, they formed the protogalaxies, and further heterogeneity within this protogalaxies, they again started collapsing to form the stars. Once these stars started forming, they continued to collapse by their gravity, and their density and temperature increased subsequently. So, depending on the temperature and the density inside the stars, different nucleosynthetic reactions started taking place, like for example, hydrogen, helium, carbon, neon, silicon, all sorts of burning started taking place. But remember that the first generation stars, they started their life with only hydrogen and helium. So, the first reactions that started taking place is hydrogen burning. And as you can see from these reactions, that hydrogen burns to form helium at the end, and in the process they generate huge amount of energy. And in second or higher generation stars, the hydrogen burned in a different way by CNO cycle, which is known as carbon, nitrogen, oxygen cycles. The second generation stars or the higher generation stars, they actually inherited some amount of carbon which was generated in a previous generation of star, but was sent back to the universe during the demise of the previous generation of star. And during this process, 12 carbon combines with 1 hydrogen and finally produces 12 carbon and 1 helium through different intermediate process products of nitrogen and carbon. So, in this process what you can see is that 12 carbon reacts and finally goes back to the star again. So, carbon in this sequence actually acts as a catalyst only to consume hydrogen and to form helium. So, please note that as I have said, these reactions are generating temperature or heat, and at the same time as the stellar cores are being more and more heavier as it forms helium, the gravitational collapse increases, but the temperature which is being generated by these reactions, they actually balances the gravitational collapse, and as long as there is a balance between this gravitational collapse and the heat or the thermal energy which tries to expand the stars remain stable or survives. So, following this hydrogen burning, as I have said, these heliums are being produced, and with further gravitational collapse, helium start burning. First 2 heliums, they fuses to form 8 beryllium. Now, there is a catch at this point here. Importantly, this 8 beryllium has a half-life of about 10 to the power minus 16 seconds. So, if 4 helium has to move on to 12 carbon, or for the safe journey of 4 helium to 12 carbon, 3 heliums must be consumed or fused very quickly, and this process is known as triple alpha process. Now, this is a bottleneck in the chain reactions or nuclear reaction chain through which the heavier elements are produced. Had this not happened, then we would not have got the heavier elements beyond helium, and the entire universe would have been composed of only hydrogen and helium. And remember, if this carbon would not have been produced, I would not have been here to discuss about the origin of elements, because we, including myself, are composed mainly of carbon, hydrogen and oxygen. So, this formation of carbon is very crucial stage in the synthesis of the heavier elements, including oxygen. Now, I will try to draw your attention to this figure out here, where in the x-axis I have plotted the mass number, and the y-axis I have plotted the binding energy per nucleon of different elements. Now, please note that this lithium, beryllium and boron has a lower binding energy per nucleon compared to helium and carbon. This means that the formation of lithium, beryllium and boron from the helium to the carbon stage is not energetically suitable. So, during this process actually the formation of lithium, beryllium and boron are skipped, and this is a very important implication in the abundances of elements in the universe and in the solar system. So, next process that operates is the carbon burning. When the temperature is about 5 to 6 into 10 to the power 8 K and density is about 5 to 10 to the power 4 gram per cc, carbon starts burning. 2 carbon fuses to form either magnesium or neon. In fact, neon is the major product of this carbon burning process. At the same time, some other elements like sodium and oxygen are also produced, and the neon produced by these reactions takes part in the subsequent reaction, and by which this oxygen is produced, which is the major product of this neon burning. But please note that neon burning is not, it does not burn in the same way as that of the previous burning processes. This 20 neon actually photodisintegrates to form 16 oxygen and 4 helium, and this 4 helium then combines with 20 neon to form 24 Mg. So, the end product actually is 220 neon produces 116 oxygen and 124 Mg. So, the stellar core at this point is composed mainly of oxygen. So, the next process that operates the stellar core is oxygen burning. The major product of the oxygen burning is silicon 28. However, other elements like magnesium, phosphorus, sulfur and 32 sulfur can be produced during this oxygen burning process. So, after the burning of this oxygen, now the stellar core is composed of mainly 28 silicon. So, the 28 silicon now attempts to burn or try to synthesize heavier elements. Now, there is a problem here. The silicon burning, that is silicon burning, is a very difficult or extremely difficult process, because the silicon has a higher atomic number. If we try to fuse two silicon atom, the extremely high Coulomb's repulsion does not allow to do that. So, silicon burning is an extremely difficult process. Therefore, in this case silicon does not burn in a similar way as the previous burning processes operate. The silicon burning operates in a very similar way as that of neon. Silicon disintegrates to form 24 neon and 4 helium, and this 4 helium again combines with 28 silicon to form 32 sulfur, and so on and so forth. And this process is where the helium or the alpha combines with the heavier elements are known as alpha process. And note that this alpha process is different from the triple alpha process that I have already discussed. So, this is during this process, this final product, actually if you can try this, you can try these reactions, like keep on adding helium to the products in these reactions, and you will end up with the final product, which is 56 nickel. Now, this 56 nickel is unstable, as its half life is just 6.075 days. So, it decays to 56 cobalt by a reaction like this, and importantly 56 cobalt is again unstable, and it decays to form 56 Fe. So, the final product of the stellar nucleosynthesis that operates inside the earth, inside the stars, is the 56 Fe. So, the fusion reactions in the stars actually stops when the iron 56 is formed, and this is the dead end of the stellar nucleosynthesis process. I will explain this a little later, why this is the dead end of the nucleosynthetic reactions or the fusion reactions in the stellar cores. Now, at this point the stellar core or the entire star actually looks like an onion shell like structure, where the successively heavier elements occur at the core, and in this case this operates this iron occurs at the core. Now, I want to emphasize one point here, that this sort of onion shell like structure occurs only in very massive stars, because in small stars the burning processes do not go beyond hydrogen or helium like as it operates in the sun. Now, there is another important process which is known as neutron capture process, by which elements heavier than iron are actually being synthesized inside these stars, and there are two different processes of neutron capture. One is the slow neutron capture process, and the other one is the rapid neutron capture process. In the slow neutron capture or the slow process, the neutrons are being produced by reactions like this, which participates in the neutron capture process in the slow processes. Now, what this slow neutron capture process actually is, I will try to explain this with an example. Let us have a look on this 62 nickel. When the 62 nickel captures one neutron, it becomes 63 nickel, but 63 nickel is beta unstable, so it decays to form 63 copper. When the 63 copper again captures one neutron, it becomes 64 copper, and this 64 copper has a branch decay. It can move on to form 64 nickel or 64 zinc. So, now if it could be possible that the 62 nickel could have captured 2 neutrons, then it would have moved to 65 nickel, and 65 nickel would have again decayed to form 65 copper. So, it is called slow process because the process is so slow that before subsequently 2 or before the 2 neutrons can be captured, after the capture of one neutron, the resultant isotope decays by beta to form a isotope of the different elements. Now, as I have said that the stellar core ends at the formation of iron and no further formation of elements takes place in the stellar core. Now, look at this figure once again, where you would see that iron has the highest binding energy per nucleon. This means that the elements which has the atomic number lower than iron would fuse to form the elements heavier in the sequence, and that can form up to iron. But formation of the elements heavier than iron will be impossible, because the elements which lies on the right hand side of iron has a lower binding energy. So, formation of elements on the right hand side of iron by nuclear fusion would mean like formation of less stable nucleus. So, the stellar core becomes iron dominant and the nucleosynthetic reaction stops, and this has a very important connotations or implications in nucleosynthetic process. Now, as I have said that the energy being generated during the nucleosynthetic reaction actually balances the gravitational collapse. Now, as the nucleosynthetic reaction stops at the formation of iron, then no energy is being generated. Therefore, the gravitational collapse becomes tremendous, and it becomes so huge that a core having a radius of about thousands of kilometers may turn out to be just 1 kilometer at the end, and the density might reach to almost the nuclear density of 3 into 10 to the power 4 gram per cc. And at this point, core rebounds and collides with the still collapsing outer part, and this generates a huge amount of shock wave, and almost the entire part of the star explodes, and this is known as supernova explosion. And imagine the quantum wave of energy that can be generated by the supernova explosion. In the first 10 seconds, the 1987 A supernova actually released energy more than 100 times the sun is expected to release in its entire lifetime of about 10 billion years. So, you can imagine the quantum of energy that can be released by supernova explosion. Now, what is the consequence of this process? These processes produces a huge amount of neutrons and protons. For example, the shock wave, the shock energy can break the nucleus of the 56 iron, and in the process it can produce actually 30 neutron and about 26 protons. Now, this abundance of avalanche of neutron initiates a nuclear reaction process which is known as rapid neutron capture process. Here is an example of this. For example, if you have 66 copper, if 66 copper captures 5 neutrons successively, it can move on to form 70 copper, which is beta unstable, and it moves on to form 70 zinc. And there is another example like 68 zinc. If it captures 2 neutrons, it can again move on to 70 zinc. Now, here lies the difference between the S process and the R process. In the S process, 68 zinc will capture 1 neutron to form 69 zinc, and then 69 zinc will move on to 69 gallium by beta decay, whereas in case of rapid neutron capture, 69 will capture 2 neutrons and will move on to 70 zinc, which is stable. And this avalanche of proton also initiates reactions like which are called P process or proton capture process. Here is an example like 72 germanium can capture 2 proton to form 74 selenium. And in the process, this proton capture actually produces elements, the isotopes or the lighter isotopes of a particular element. Remember that the P process is less, it does not operate as commonly as the neutron capture process because of the proton-proton repulsion during the proton capture process. Another important process operates here, which is the proton process or proton capture process. Here is an example where you can see that 72 germanium can capture 2 protons to form 74 selenium. The proton capture process actually produces lighter isotopes of the elements. For example, it produces 74, where the heavier isotopes of selenium is 76 and 77. Now, remember that the P process is less likely to occur compared to neutron capture process, because when the nucleus tries to capture proton, there is a huge proton-proton Coulomb's repulsions. So, we have discussed that during the Big Bang nucleosynthesis, hydrogen and helium are the main product and lithium is produced in a trace quantity. During the stellar nucleosynthesis within the earth, most of the elements up to iron has been produced or being synthesized even today. The heavier elements or the elements heavier than iron are being synthesized or were synthesized by mainly neutron capture processes, either within the stellar core or during the explosive nucleosynthesis as well as during proton capture. However, elements like lithium, beryllium and boron, they were not synthesized by any of these processes. Now, how these elements have been synthesized in the universe? Now, there is an important observation which shows that the concentration of these elements in the cosmic rays is quite high. Cosmic rays are actually high energy atomic or subatomic particles traveling at the speed of light. Now, the high concentration of these elements in the cosmic rays suggests that they might have been produced in the intergalactic spaces. Now, how are they being synthesized? Actually, the high velocity cosmic particles, when they heat the atoms in the intergalactic space, the spallation of the nucleus takes place, and this nuclear spallation results in the formation of these elements. For example, when a high energy carbon nucleus heats the hydrogen atom, it forms the nucleus of the carbon breaks down to form a lithium and a helium particles. And most of this process involves the spallation due to the collision of carbon, nitrogen and oxygen nucleus with the atomic materials or the atoms in the intergalactic space. So, up till now what we have seen is that different elements are being synthesized in different parts of the universe by different processes in different astrophysical conditions. Now, the question is how these elements are distributed in different parts of the universe, or what is the abundances of these elements in the universe and in the solar system. So, in the next slide I will show you the abundances of these elements in the solar system. Now, look at the concentrations, the abundances of elements in the solar system. So, these abundances are plotted with respect to 10 to the power 6 silicon atom. As you can see, there are certain important features. For example, hydrogen and helium is by far most abundant elements in the solar system, whereas lithium, beryllium, boron are among the least abundant elements, or their concentration is much lower compared to the nearest neighbor. And the concentration of iron is very high compared to its neighbor. On the other hand, the concentration of the first 50 elements that decreases almost exponentially, and the concentration of the elements beyond 50 are very low and do not change appreciably with atomic number. And this can be explained with our understanding on the origin of the different elements. We have discussed that hydrogen and helium are the first primordial elements that formed during the Big Bang nucleosynthesis. So, they are the first elements, and therefore, they formed by the first Big Bang processes. Therefore, their concentration is expectedly to be quite high in the universe and in the solar system. On the contrary, we have seen that lithium, beryllium and boron, they do not form in the major processes of nucleosynthesis like the Big Bang, stellar or explosive nucleosynthesis. They are produced only by galactic nucleosynthesis processes in the intergalactic space. So, their concentration is expected to be quite low. The iron concentration is very high compared to the other elements. We have discussed that iron is the final product of the stellar core, particularly in the large mass stars, and the stellar core stops at iron formation. So, therefore, iron is again very high in abundance. The rapid decrease in the concentration of the elements up to 50 perhaps reflects the gradual increase in the complexities or difficulties in the synthesis of these elements. And the elements beyond 50, we have discussed that these elements are mainly synthesized by neutron capture either within the earth and mostly during the explosive nucleosynthesis, and that is precisely why their concentration is very low, as because they form only in a very, very specific astrophysical conditions. Now, with this understanding or idea about the average composition of the solar system, now let us look at the composition of the earth as a whole. Now, see the concentration or the compositions of earth, where we have iron is the most dominant phase, followed by oxygen, then silicon, magnesium and nickel, some amount of calcium, aluminum, and rest of the elements their concentration is much less than 1%. Now, why earth has a high concentration or much highest concentration of iron, whereas the concentration of hydrogen, helium and and the other elements which are very abundant in the solar system, but they are practically do not figure in the first 10 or 20 elements in the earth. Now, to understand this difference in the composition or abundance of the elements in the earth and in the solar system, we need to have a bit understanding on the formation of the earth. Although I will not go into the details in the discussion discussing the origin of the earth and the planets, the common understanding that we have is that planets form from disc-shaped solar nebula, which are comprised of materials left over after the formation of the sun. Now, the hot nebular gases, they actually condense to form some solids which finally accreted to form the planets. Now, the inner parts of the solar nebula, actually from where the terrestrial planets including our earth were formed, they had a very high temperature during the accretionary process, as because they are very close to the sun. So, this very high temperature mostly they volatilize the volatile elements, and which could not condense back to the planets which are close to the sun. However, the stars the planets which are far away from the sun, in those stars the volatile elements could condense on the planets, and the concentration of the volatile elements in those planets are much higher. However, the concentration of these volatile elements are much less in the earth. Remember one thing here, that the concentration of oxygen is quite high in the earth, unlike carbon. Carbon is a very important component in the solar system, but it is not that high in concentration, just only 0.07% in the earth. So, compared to oxygen, its concentration is extremely low in the earth. Now, what could be the reason behind this? The reason is that carbon was also lost mainly in the form of methane, which was volatilized during the accretionary process, whereas a large part of oxygen was stuck in the silicate structure, and you know that silicates have a high melting point. So, they could not be volatilized easily during the accretionary process, although they were close to the sun. So, that is precisely why the earth is composed mainly of the heavier elements. The volatile elements are almost negligible, their concentration is very, very low in the earth. Now, let us have a look on the composition or the abundances of the elements in the atmosphere. Atmosphere is a very important component of the Earth system. So, its composition and its evolution is very important, particularly also to understand the evolution of life in the Earth. So, let us have a look on the composition of the atmosphere. Before that, the Earth's atmosphere is actually considered to be up to 100 kilometer altitude, and beyond that it is considered to be the outer space. So, what are the sources of different elements that we see in atmosphere, or that can contribute elements to the atmosphere, are of course the residual gases which remain there after the formation of the solid earth, the shock release, that means the meteoritic impacts, they might have released some gases from the earth which can be present in the atmosphere. Then the extraterrestrial contributions, again coming from the meteorites and other impact materials. Then mantle degassing, we know that the mantle quite often produces magma which comes up on the surface, and along with this magma they bring out a lot of volatiles or volcanic gases. So, that can also contribute to the atmosphere. And there are organic activity we know which are also releasing different materials to the atmosphere. And another important thing is radioactive decay. For example, potassium decays to form argon, which is being introduced to the atmosphere. Similarly, uranium and thorium are also releasing helium, which is being contributed to the atmosphere. Now, this is a composition, a present day composition of the atmosphere. What you see is that nitrogen and oxygen, they constitute more than about 99% of the present day atmosphere. And the next abundant element is argon, then carbon, followed by helium. So, argon and helium, these two are quite abundant elements in the atmosphere after nitrogen and oxygen. Now, why the present day composition is like this? So, before that, as we can see from these figures, it clearly shows that the present day atmospheric composition is certainly not the original one, and this is a modified or a secondary atmosphere. Had this been the original atmosphere formed after the accretion of the earth, then we would have expected more of volatile components, maybe in an increasing order, in a decreasing order like hydrogen, helium, carbon, oxygen. But as I have said, that these elements are not that abundant even in the earth, so they are not at all abundant in the atmosphere as well. But the question is, why nitrogen, oxygen, argon and helium are so abundant? Now, the main important things or contributors are the bacteria like the denitrifying bacteria, which actually reduces the organic matters in the earth and produces nitrogen, which is being contributed to the atmosphere. Oxygen, a large part of this oxygen is being released by photosynthetic reactions. So, that is precisely why this nitrogen and oxygen are quite abundant in the atmosphere. So, they are all biogenic in origin. Whereas, if you look at this argon, which is very high in concentration, its main contributor is potassium 40, which decays to form 40 argon. Now, why and how do we know that the contributor of argon is actually 40 potassium? If we look at the concentration of argon 40 and argon 39, the ratio, we see this is much higher compared to what is expected. So, this implies that the 40 argon was contributed by actually 40 potassium. And we say that this residence time is forever, that means argon actually resides forever. The main reason is argon is reasonably heavy, so it is not lost in the outside the atmosphere in the outer space, because being heavy. At the same time, argon does not form strong bonds with any other elements, so it does not come back to the earth again. So, its concentration is its residence time, that means for how long it stays there is forever, whereas helium has a certain half life, and the major contributor of helium, as I have already said, is uranium and thorium, which produces helium through radioactive decay. Now, after this, let us have a look on the composition of the hydrosphere. Now, the hydrosphere actually comprises of the different water reservoirs, of which ocean is the most important thing. Like it contributes about 96.83% by volume of all the waters on the earth's surface, and the other reservoirs of water are like oceans. Besides oceans are rivers, ice caps, groundwater, lakes, so on and so forth. Now, we need to understand what are the factors that control the compositions of the different water reservoirs. Actually, elements which are soluble in water, they would be in high concentration in our hydrosphere, and the solubility depends on many factors, and one of them is the ionic potential, which is actually the ionic charge by radius. This controls the solubility of many elements in the different reservoirs or different waters. So, if the ionic potential of an element or an ion is quite low, that means it will not form that will indicate it will not form strong bond with oxygen, and as it does not form strong bond with oxygen, it will not be soluble, it will be highly soluble in water, whereas the cations with very high ionic potential, they form strong bonds with oxygen. but when such compounds they try to combine together, the strong cation-cation repulsion makes them again soluble too. For example, sulfur forms a very strong bond with oxygen, but when two sulfate ions they try to come together, the sulfate-sulfate reductions make them, they repulse each, the repulsion results in this solution or dissolution of sulfate in water. So, that is how the concentration of the different elements are controlled in the different reservoirs. Here we show the compositions or comparison of the compositions of different reservoirs. Like you see, this chlorine concentration in sea water is extremely high, whereas river water is much less. And note that the concentrations of different ions like sulfate, bicarbonate, carbonate are extremely high in the different reservoirs, particularly in seawater. So, the elements has been distributed in the different water reservoirs in different way, and their compositions varies, therefore, their composition varies in different reservoirs. So, now I will summarize today's discussion. What you have seen is that Big Bang is considered to be the beginning of the universe, and we practically do not have any idea about what was before this Big Bang. So, the universe is thought to have started from the Big Bang, and we have also seen that the elements formed by different processes, and there is not a single process by which they could have been synthesized, and elements are also being synthesized today in different stars, including our star, including our sun. And the processes by which, or the mechanisms by which the elements form, have important control on the abundances of the elements in the solar system and in the different parts of the earth as well. So, the more difficult or complicated the process of formation is, less is the abundance of the elements in the universe. And the formation of the elements, although have a clear control on the solar system abundance, the abundance of these elements in the earth is quite different from that of the solar system because of different reasons. And the concentration of elements or abundance of elements in our atmosphere is also different from the average abundance of the earth system, and the concentration of these elements in this atmosphere depends on the interplay of the earth atmosphere biosphere interactions, and the concentration or abundance of elements in waters is controlled mainly by the solubility of the elements, their residence time, and the supply of elements in the water basins or the water reservoirs. So, thank you very much.